Hi guys, welcome to this third video looking at the analysis of athlete monitoring data. In this video, we're going to start looking at random slopes linear mixed models. And in order to do this tutorial, you'll need to open Monitoring Viz 2 and the monitoring script in SAS. So if we look at Monitoring Viz 2, this is essentially the situation we left ourselves in at the end of the last video. And what we've done is we've created a linear mixed model that has an intercept and it has a single covariate, which is the mean-centered sleep. And this means that for every unit increase in sleep, we know there should be a certain increase in daily wellness. And so we can create an intercept, the overall intercept. And then because we know there's clustering between athletes, or within athletes, sorry, we can create these random intercepts which must be at the same gradient as the mean intercept. So because there's a few more green spots here, we know that we can put the green line up there. Likewise, there's a lot more yellow down at the bottom. So we put the yellow one down at the bottom. But what we said in the last video was that perhaps restricting these lines to be the same gradient as the intercept line potentially isn't the most accurate way of doing things. And so in this video, what we're going to do is we're going to turn this into random slopes. So this is a random intercept model, and a random slope model just says that these slopes can vary. So we now do not need to have the same gradient as the random intercept model. So if we move into SAS, we need to go down to the model that starts on line 70. In this model, you can see the first line's the same as normal. The second one and the third are both exactly the same as well. However, now, rather than just having random intercept, we now have random intercept and MC sleep. And what this is going to do is this is going to create a random intercept for each participant, but also a random slope based on their mean-centered sleep situation. And we use type equals un to allow any type of variance and covariance element to be used. There's various other ones that you could play about with. For example, various components means there's no covariance between these two measures. And then there's ones like auto-regression, which allow you to reduce the impact of previous measures. We're just going to stick to type equals un for now, and you can play about with them yourselves. So the estimation of the 1 hour sleep and the intercept are exactly the same. However, now when we're estimating the athlete's individual measures, we now need to add an adjustment for their own mean-centered sleep. So we take one portion of the intercept, one portion of MC sleep at the mean level, and then make an adjustment for the subject or the participant for both the intercept and the mean-centered sleep. And we do that for all 4 athletes that we said we were going to look at. This should be athlete 13, 13, 8. So let's run that model. First off, check the log, and you can see there's no errors or warnings. Same number of class levels. Still got the 450 odd missing observations. We've met the convergence criteria. And now you can see there is an extra element within the covariance parameters. So between participant, you can see there's quite a large element. This is now the between participant variation in the influence of sleep on daily wellness for this 2-2. So that's the second part. And then we've got the within participant variation as well. You can see this number is still quite small for the sleep. And then when we have two measures with an unstructured relationship, we then get a covariance parameter for them. We don't need to worry too much about what that means. We're always interested in these diagonal elements. So anything that's a 1, 1, 2, 2, 3, 3, 4, 4, etc. We can see that the influence of sleep is still significant. It's now slightly increased to a 3% difference in the subsequent day's wellness score. And now we can see when we look at the solution for random effects that there is now a mean-centered sleep element as well, where we can take an adjustment. So for example, we would add 2.35 for every unit of sleep compared to the normal amount, the mean amount for participant 2, and we'd subtract 1.05 for participant 10. And we get this for all of the participants. If we move to the estimates, we can now see the influence of a 1 hour sleep. We've got the intercept as it was before for -6 hours of sleep and +8 hours of sleep. And then we've got all of the athletes' individual values. And again, there's still a little bit of outline, a little bit of an outlier at the top end of the QQ plot and the histogram, but generally it looks pretty good. So let's go back to the visualization to see how that looks. First of all, we'll remove all of the random intercepts and check how the new random slope intercept looks relative to the random intercept model. And you can see that the new random slope model has a slightly steeper slope. So with the random intercept coming at the top part of the line on the left-hand side and the bottom part of the line on the right-hand side, that just means that the random slope intercept is slightly steeper. Let's get rid of the random intercept slope. And let's focus on athlete 9 again. And what I'll do is add athlete 9's random intercept first. So we can see that the random intercept for athlete 9 came across in this direction. It was probably at too shallow an angle. And we said that potentially something that came more in this diagonal angle was probably a bit better for athlete 9. So let's have a look at what the random slope has done. And you can see that it is much, much steeper, not just steeper than the random intercept, but steeper than the mean for the random slope, and really captures the picture of what's happening with the with athlete 9's data much better than either of the other two elements. So if we take away both of those two elements, the random slopes in mean intercept and the random intercept, you can see that's a pretty good line of fit for the for athlete 9. Next, we can have a look at athlete 11. And here again, we said that potentially a flatter line would be more appropriate, maybe even verging on a negative sloping line, although I doubt that will happen. You can see that the random intercept and the random slope, like grand mean intercept, are fairly similar here in how they don't really show the data. And when you look at the random slope, it's just flat. In fact, there is possibly a slight negative element to it, but it's mainly just flat. And this falls in line with what we suggested could happen, but it gives a better understanding of what's actually going on with the data. So again, if I take both of them away, you can see it's not a bad line of best fit, to be fair. for the data that is there. Okay, athlete 12. So athlete 12, we can see the random slope is a long way below it, the grand mean random slope, and the way the random intercept accounted for this was just to increase the level of the intercept and try and cover it in that same way because we couldn't change the slope. And we said the slope might be a bit flatter if it could be. So let's have a look at how that looks. And that's worked out pretty much as we expected. The slopes ended up being a bit flatter, but actually the intercepts ended up in a fairly similar place, which shows that the random intercept for this was actually not too bad an effort. Finally, athlete 13. And athlete 13, we said obviously the random intercept moved downwards because all the data was below the grand mean intercept. And again, this could possibly be a little bit flatter when a random slope occurs. So we'll have a look at that and see if that's what's happened. And actually it's become a bit steeper just because of the way it's worked out. So because of these values down here, it's become a bit steeper. So I got that one wrong, but you can see how it probably fits the data better than the random intercept did. And that's basically all for this one. I just wanted to show you how a random slope model works. What we'll do in the next video is have a recap of all three types of random intercept, random slope model with this data before moving on to the next section.